Alright, hell yeah. So what we have here is a pulley. And what I want to do is reference this video for other rotational problems. You know what I mean? If we have 50 kilograms on this side and 100 kilograms on this side, you know what I mean? Hey, we have mass, so and we have an earth underneath us, so we have a force that's going to be mg over here. That's going to be 50 times 10 or 500 newtons. And over here we're going to have 100 times 10. That's going to be that mg. And we have 1,000 newtons. Now what I would like to say is like, hey, you know what I mean, since we have a 500 newtons on this side of the pulley and 1,000 over here, I would like to say that, hey, we just have a net 500 Newton driving force. So what I want to do is quickly look at a problem like this and be like, oh, I see that. I have a 500 out of these two numbers, one on one side, one on the other. I have a net force on this side of 500 newtons. So I have a driving force of 500 newtons. Now the only thing that you got to be careful about with this problem is you have to use this driving force on both masses. So if I do F equals ma, I would say I have a driving force of 500 newtons, and then the total mass is 150 kilograms, and I can find my acceleration. And for this problem, it's 500 divided by 150, and that's going to be 6.6. Sweet. No, hell no. Sorry about that. It's going to be 3.3. I was thinking about a different problem. Okay, so we got 3.3 meters per second. So yeah, it's kind of interesting. It's this third of, you know, gravity is 10 meters per second every second. This is going to be a third as slow. Okay, sweet. You know what I mean? And then I thought I was done. I thought I could use this method just for all problems, but that wasn't the case. Because now what we're going to do is we're going to take our pulley. Well, before we do a complex example, we should do this one the textbook way. Like, how do you actually do this? If we have 50 kilograms, 100 kilograms, you want to do free body diagrams. You want to chop these things, you know what I mean, and then put them into outer space, and then just kind of see what's going on with them. You know what I mean? Hey, back on Earth, it's a mass, and we got an Earth underneath us, so Kepler's equation, we have... you know what I mean, the force of gravity is gravitational constant, this mass times the mass of the Earth divided by the radius of the Earth squared. But these three things are just g, so we get mg. You know what I mean? And so hell yeah. So we know that we have a force of gravity on this one, 50 times 10, and that's going to be that 500 newtons. Alright, so the other thing that we know about this is that we have a tension force up. So we do that tension force. Cool. And maybe that's about it for now. We'll go over to this other one. And so we have 1,000 newtons down. And then we also have a tension force. Now on the pulley problems, you do have continuity. The continuity is that the tension in the cord is going to be the same. And then also the accelerations are going to be the same. Cool. And then for these problems, you know what I mean, I think they're way easier, at least do once, where you take this thing that loops around something, and then you just put it on a flat surface. Just like this. And then you start putting on the forces. So you would put this force over here of 1,000 newtons. That's going to be the mass of 100 times gravity, mg. And then you would put this force this way of 500 newtons, you know what I mean? Because it's kind of going in the opposite direction. But we stretched it out, and now this makes just a lot more sense because we have that force net of 500 newtons going that way, and we can use our F equals ma. And even here, it's way easier to see, hey, we got that 500 newtons on this total mass. Of 150 kilograms, and we want to find the acceleration, and that's going to be 3.3. But so when you do the technical perspective of like taking free body diagrams of both these, it's very important to at least, you know, show what's if you can see it, if you can see, oh hell yeah, this thing's going to move this way. Like, pick that direction as positive. Because even when we laid it out here, hey, this was going to be the positive direction. This was going to be the negative direction. So if we sum forces about this path, we would say we have 1,000 newtons going positive minus 500 newtons. And, you know, we're doing the F equals ma equation. We're summing the forces, and then we're going to say, hey, that's equal to the mass, 150 kilograms, times the acceleration. So, so that problem jives this way. Now, it'll jive. The only kicker, and I think this is a good one for me, is like, hey, I'm just going to designate this to the positive direction. But then, if this motion is positive, I go over here. Up here, this motion must be positive. So we say, hey, this is the positive direction on this side, and this is positive. But I would label it on my graph, on the diagram like this, and then go over to my free body diagram. Because now when I sum forces, I'm going to say, hey, we got a t. I'm always going to try to do the positive one first. So we have t minus 500. That's going to, so what we're doing is F equals ma. So we're summing the forces. So we have t in the positive direction minus 500 is equal to this mass, you know, because we chopped it out of the free body diagram. So it's going to be 50 times the acceleration. Okay, now we go over to this one. This one says that we have 1,000 newtons driving minus tension is equal to this 100 kilograms. That's 50. And so we have 100 times the acceleration. Now, I definitely already said that the accelerations are going to be the same, so these A's are the same. We could have designated this to be mass A and this to be mass B, and maybe, you know, for some problems you have to designate this A and B. But we are saying acceleration A is either acceleration B is equal to just A. So we'll get rid of those. Okay, hell yeah. So now we need to solve for acceleration. You know what I mean? We got two equations, 1 and 2 unknowns, the tension and the acceleration. So we're just going to solve for this tension right here. And a couple ways to do it. There's a negative t over here, you know what I mean? So you can do this kind of a creative way. It's like, well, maybe I'll solve for negative t. I'm going to bring t over here and then this 50. So I got negative 500 minus this 50a is equal to, bring the t over here, it's negative t. So see this negative? I can throw that right into there, and then I don't have to like do too many steps. So here we have 1,000 minus, we're going to put it in this. So minus 500 minus 50a is equal to 100a. So now we'll bring this 50a over here. We're going to get 150a, and then we're going to subtract these two. We get 500. So now a is 500 divided by 150, and we get that classic 3.3. Now for this, what I'm going to do also is go back and solve for tension. You know what I mean? Because tension, how about this? Tension is equal to 50a minus or plus 500. Cool, so that's going to be the tension, and that's going to be 50 times 3.3 plus 500, and so let's do that. I got 3.3 in my calculator times 50 plus 500, and we get a tension of 666, you know what I mean? And so, yeah, that's kind of interesting. So if you, and this is fascinating, because if you had to hold this thing, just imagine you're like holding it, and if it was balanced, you know what I mean? If you had something that had 75 kilograms on both sides, well, you would be holding 150 kilograms. But because you're holding something that's unbalanced, that motion is causing you not to feel that. It would be the same scenario as if, like, hey, you're holding this pulley that you have a massless rope on this side, like spooled, and then you have, let's say, just 150 kilograms, just like our problem, and you have to hold this. Well, this is basically going to fall, free fall, and, you know, theoretically, you're not going to feel a thing holding on to that. So that's the scenario there. So it's sometimes good to take, like, oh, I don't see that. If this is 50 and this is 100, why isn't this, why am I not feeling 150 kilograms, you know what I mean? Well, it's because you have moving mass. Well, let's just leave it at that. But then if you take it to a farther example, you're like, oh, yeah, this mass is in free fall. I wouldn't feel a thing. Okay, cool. So let's keep that in mind. And now this tension is in both ropes. So if we wanted to know how much we'd actually, you know what I mean, have to hold this up, you have two T's right here. And so it would be that times 2. So if this was 150 kilograms, we would have to hold up 1,500 newtons. But we're not. We only have to hold up 1,300, 1,300 newtons. Cool. So yeah, so what we're going to do now is we're going to take this problem and make it the more complicated. Because I was trying to use just this of saying, okay, I want to see a problem where I have some sort of mass over here and then maybe some sort of mass over here. And then I say, okay, I have a driving force that's maybe this mass minus, the mg of this, the mg of this one minus the mg of that one, and that's going to be my driving force, kind of like my force net, and I get how it's operating on the total mass, you know what I mean? But that only works if like, hey, this doesn't move. But there's plenty of problems in rotational problems like this, like the whole like toilet paper roll, you know what I mean, or just like a disc wound up with string, and then it's like unwinding itself. Well, hey, you're trying to take this pivot point here as like, because what I was trying to do was turn this problem into a problem that I could kind of grasp, and actually, but with this, at a couple seconds later, or maybe even just 1 second later, that point moves. Because I wanted to take this problem and say, hey, well, let's just turn it into a pivot, and hey, we got some mass of this. We could just say that we have some mass of this disc that kind of looks like this, and we can turn this into a bar, and maybe this bar just swings around this pivot point. Well, sure, that's cool, but this pivot point is constantly moving, and this pivot point is accelerating. Like, so if you take this disc, it doesn't fall in free fall. Like, if you just did this, this would fall at 10 meters per second squared. But this disc, we run the calculations, and it's 3 halves. Is that right? Is it 3 halves? No, it's 2/3. Sorry about that. Yeah, it's less than gravity, so it's going to be 0.6, or I mean, it's going to be a 2/3 g. So we're going to have 6.6, meters per second squared on this one. You know what I mean? So what I was doing was like, hey, I was turning this into this problem where it's just like, okay, I got some driving forces, and now like and then I would turn this into a continuity problem. You know what I mean? Like, both these masses, if they weren't connected, would be after a second they'd be right down here, but they're not. Like this mass is up here, and then this mass might be actually lower, you know what I mean? So this mass seems to be going slower, this mass seems to be going faster. But what I want to do is turn this problem into this, but I came up with a hiccup of not adding the acceleration, not saying this whole system is falling. Because check this out. Because if I had this scenario of just like a pivot and a mass, like, cool, like, sure, it's going to start to rotate, right? You know what I mean? But guess what? Let's say this is connected to a bar, and I'm just holding it. And yeah, I would expect this to rotate. But now let's say I just drop the bar. You know what I mean? So now I have a bar and a mass, and it's just falling in space. You know what I mean? Well, hell no, it's not going to rotate. And I think that's fascinating. But then you get to the, you know what I mean? So, and you can turn this problem, like, hopefully you can actually solve it fairly simply. We have a mass, a force on a mass, and if this is a really long, you know what I mean? Like a really long, well, hell yeah, this thing is just going to want to do what it normally does, is just fall in free fall. And so it's just going to be right there. Sure, due to continuity, it's going to be a little bit inside. But for like maybe 1 second, if this is hella long, like the acceleration is going to be 10. So you can find that. You know what I mean? That's what that's going to be. But if you drop this and you're just an observer, it's kind of like relative kind of like frames of reference, and you're falling with this, well, hell no, you're not going to see this move at all. It's going to appear stationary. Even if you're both accelerating, hey, you're both accelerating, you know what I mean? It seems like sometimes like when things are moving at constant velocity, you know what I mean, maybe that's when you don't see changes in acceleration or forces. But yeah, so this is just fascinating because this comes up a lot. Because I can't treat this roll of toilet paper rolling down as just a pivot right here and then expect to find the angular, because like I want to know like, hey, what's the omega at 1 second? And then what I do with problems, and this is another kind of tip, is like, hey, the velocity is 0 right off the bat, and then your angular velocity is 0. So cool, run the problem for 1 second, and you know what I mean, whatever your angular acceleration is, well, you can just say after 1 second that's just what your angular velocity is. You know what I mean? So you could do that. Now, if I did it from this scenario, you know what I mean, using that method, I could figure out what forces were on here and what linear accelerations they would have, and then due to continuity I could figure out the placement of this, and then I could figure out the angular velocity. That's what I want to do for problems, just because it's kind of a fun way to visualize it. But that's not going to be the case if this is also falling. You know what I mean? Because if this is stationary and I get something like this after 1 second, and I come down here and do that same scenario and then have it fall, free fall, well, it's not going to spin at all. So what we're going to go over is that halfway point is just like, well, what if it's not free falling at 10 meters per second squared? What if this thing is just falling at 5 meters per second squared? So it's gonna increase in velocity from 0 to 5 after 1 second, to 10 to 15 to 20. That's acceleration. And then I want to know maybe what this omega is. And we can see, even just by this example, that, you know what I mean, well, it should be half. So that's what we're like. In this example, if we're saying, if this is a fixed pivot and it goes down here, maybe 1 radian, or this looks like half a radian. So we got a half a radian per second. But if we had it in free fall, we would have 0 radians per second after 1 second, because you just won't have any acceleration. And here you have an angular acceleration if it looks like a half a radian or 0.5 radians per second, you know what I mean? Or 0.5 radians per second squared. Cool. But if this thing's falling at half of gravity, or 5 meters per second, it should be halfway in between. We wouldn't see it like this. We would probably see it like this. So this is where it would be. And we would say that the angular acceleration is 0.25 radians per second. And then, so, you know, for problems like a Pulley problem, if I said that there was 500 newtons of driving force, you know what I mean, on this problem, well, let's do the scenario where you just release this. So now we're going to pretend like we just dropped this out of the sky. You know what I mean? Could we say we have 500 newtons driving force? Hell no, we have 0 newtons driving force. We already showed that if this whole system is falling, it won't be doing this. You know what I mean? Yeah. And even me, it's just like I can say that, but then I can't say words after that. I just have to be like, hey, now we need to go on to the next thing. You know what I mean? The further explanation will come later. You know, from exploring this stuff. So what we're going to say is that if it's static, we already found that the acceleration on this was 3.3. If it's free falling, the acceleration is 0. So now we're going to do 5 meters per second. Well, we're going to, you know, I mean, take this to a, well, I guess we can't take it to another planet. Somehow we would have to put it in a machine, like on a track, and it would change velocity. In 1 second, it would be 5 meters per second. And I love, we'll take a step back for this, because it's just so fascinating. So our velocity is going to be 0. After 1 second, it's going to be 5 meters per second. Now, do a little integration. This is easy integration, where you say, like, hey, what, maybe like ask the question, how far did you go? Well, you have to like, hey, we were going 0 velocity here, but we're going 5 meters per second after a second. You can't say we were going 5 meters per second that whole second. I mean, and you can't say we were going 0 meters per second. So you have to find the average velocity. So we were going, average velocity is 2.5 meters per second. And we did that for a second, so we went 2.5 meters. Cool. And then in the next second, well, we're going to go 10 meters per second. So our average velocity is 7.5 meters per second. We did that for a second. Whoa. We just increased another distance of 7.5. So after 2 seconds, our total distance is 10 meters. So you would have to make a machine to like get this thing. After 1 second, it's got to be at 2.5 meters, and then at another second, it's got to be 10 meters. And this is half of gravity. So if we doubled it, every second you're going to fall 5 meters. That's quite a ways. And in 2 seconds, you're going to fall 20 meters. That's a pretty big cliff to jump off into some water. All right, hell yeah. So now we kind of have this representation that if this whole system falls, hey, this acceleration is going to be less. If it falls free fall, it's going to be 0. If it's stationary, it's going to be 3.3. And then I guess just before we move on to the actual problems, we should do all scenarios. So stationary, it's going to be 3.3. Free falling, the acceleration is going to be 0. If we fall at 5 meters per second, the acceleration is going to be halfway in between, 1.6. Okay, but that's falling this way. You know what I mean? How about we fall this way? How about you make a machine to drag this thing up at the same rate as never mind. Well, yeah, sure. Let's do that. So if you're able to drag it up at the same rate as gravity, well, I think it just doubles. This would just go much faster. It's just like, oh hell no, you know what I mean? So, but what I wanted to talk about is the weird one. If you actually drag this thing the other way, these things will go the opposite direction. Now, it works better if you actually use like a teeter-totter. And this is a video that I want to do. You know what I mean? Have a little pivot, and then have a teeter-totter of a 50 and 100, or you know what I mean? Just a double mass over here and a mass over here. And so, so if I'm stationary with it, this is going to fall that way. If I just drop it, they're going to stay the same, and it's going to just fall to the floor like that. Okay. And then the other scenario is that I could bring it. I could take it to the floor, and then bring it up real fast. And if I do that, this one's going to drop much faster. That's the one I explained. But it's this last one that's fascinating. If I actually pull this thing to the ground, if I pull this thing to the ground twice as fast as gravity, like, because if I just have it going at an acceleration of gravity, it's not going to move. But if I do 2 times gravity, if I actually pull it down, it's the same scenario flipped. It's like you know, the Earth flipped upside down, and now here you're basically saying that here's our force of gravity on these. And then this side will go that direction. You know what I mean? So visually, if we look at this, this side is going to fall this direction. You know what I mean? If it's just a static. But we could do a scenario where we pull this down twice of gravity, and this one will go up. And it's the same. It's the same thing of just saying, hey, it's stationary, but then gravity is moving down. So I think that is a very fascinating one. Okay, so now we're just going to kind of get technical for the rest of this video. Cool. So, because, yeah, I don't know. This one did not make sense to me. I actually had to rattle my brain quite a bit tonight to actually get anywhere near kind of what's going on. So we're going to do this little sign and say, hey, we have an acceleration of 5 meters per second. This is going to be the whole system. This has nothing to do with what these two things are doing. We don't know that yet. You know what I mean? But we do know we set the whole system up in a frame where it's gonna move like that. Okay, so from the technical perspective, we're still going to assume that, hey, this thing is gonna go this direction, and we're gonna say that's gonna be the positive direction. And if this goes this way, this is gonna be the positive direction. Cool. So we're gonna do the free body diagram, and I'll just do it right underneath because that's kind of visual. And so we still haven't. This is still made of mass. So that was kind of the interesting thing, is because I wanted to say, oh, the forces are less. You know what I mean? Well, yes and no. You know what I mean? The tension is less, but because this is still a mass, Kepler's equation still applies. Your force of gravity. If you identify this mass next to the mass of the Earth, that never goes away. You know what I mean? So we have the force of gravity. So we at least have one force on here, and that's going to be the force of gravity. And that's going to be, you know what I mean? Force of gravity is this mass. Gravitational constant, this mass of the Earth, divided by the radius of the Earth squared. But again, all these three things are just a number, and it's 10. You know what I mean? And so we have m times 10. You know what I mean? Classically mg. Cool. So here, this one's going to be 50. This one's going to be 100 kilograms. So we're going to have a force of, you know what I mean, 50 times 10. I'm just going to write it as 500 newtons. Kind of keep it simple. We still have a tension right here. Okay, so now we're going to go over to this mass. We're going to have that 1,000 newtons because it's made of mass. It's next to the Earth. Okay, now we're going to do a tension up. Cool. So this direction is positive, and this direction is positive in this diagram. Okay, now we go to our equation F equals ma, and obviously we're just summing the forces in one direction. We're not worried about any other direction. I'm just going to do a generic F equals ma, just one path. Okay, and then we're just going to sum forces. I always do the positive ones first, so let's do tension minus 500. And now here we got to, you know, we're only focused on this. Like we chopped it out of outer space. So that's kind of the cool thing about free body diagrams. You can just chop anywhere and then say, oh, it's made of mass. Well, I took this thing and it's just in deep space. You know what I mean? But then I go back and it has the same properties on Earth. So I say, oh, I identified a force on it. And I don't know, whatever. But anyway, so so here's the kicker on this side, is that we have this 50 kilograms. So we're going to say 50. But what's our acceleration term? This is where I kind of got stumped. I was just like, oh, I never thought acceleration could be a you know what I mean, I don't know if it's because it's a vector quantity or like a summation. You know what I mean? You're just like over here we sum the forces. Like here you get to sum the acceleration, and I think I've seen that written this way. You know, sum of the forces in the y direction is equal to mass times the sum of the accelerations in the y direction. And I would like to know where I actually saw that, because I've like, it's just surprising that I've never used this. I don't think ever. I don't know. I swear. But anyway, because dynamics was never my strong suit. That's why it's so fascinating to learn dynamics just later on in life. Okay, so this acceleration, well, we know this is going the whole thing, like, okay, because this whole system is going this direction. This mass is part of that system. This mass is going 5 meters per second this way, and that is the negative direction. So we got to go -5. But then we have to leave room for, like, hey, is it doing something like this? Is it accelerating along this path? And that's where I'm just going to say, well, I think it still is. I think it's going to go positive. So I'm just going to say, hey, this is going to go positive A. So there you go. And now we'll do the same thing over here. We have that driving force in the positive direction. So we have 1,000 minus the tension. And so, sorry, this positive is, So there you go. So this is the positive direction. This is the positive direction. That was just confusing having them up there. Okay, but those applied to that chart. They just got in the way of this chart. Okay, so we have this 1,000 minus t, and this is going to equal our mass. You know what I mean? F equals ma, 100. And then this is actually, this whole thing is going 5 meters per second, and that is in the positive direction. So this one is positive 5 plus the acceleration. So there it is. You know what I mean? So that's from the technical perspective. And I don't mind doing technical problems as long as I'm using it to learn something about the fundamentals of what's going on. But sometimes, you know, doing things in a technical way, you lose all knowledge of what the hell's going on. Okay, so we got 2 equations, 2 unknowns. We want to solve for acceleration. And, you know what I mean, hey, like I never do this. You know what I mean? I don't. I always just like solve for like one variable and then shove it into the equation. But you know what I mean? We gotta get better at things. So because we have a t here, but then we have a negative t here. So cool. We can just add these equations together. So t plus negative t is 0. Cool. And then negative 50 plus 1,000 is 500. So there you go. And now we're going to add these parts of the equations. I might as well do this. This is negative 250 plus 50a. And this is 500 plus 100a. So let's add these up. So it looks like we got 250 plus 150. And look how simple that was. Okay, so now we're going to take this over there. So we got 250 is equal to 150a. And we can solve for a. That's going to be 250 divided by 150. And so, hell yeah, 250 divided by 150. This is 1.6. And guess what? Multiplied by 2, this is going to be a half. So our acceleration, when this wasn't moving, was 3.3. And now because it's moved, the whole system's moving at 5 meters per second, this acceleration is 1.6. Now for, well, let's find the tension. You know what I mean? Well, it's all buggered up in here, but we got tension is equal to, we're just going to take that 500 to the other side, minus, this is 250, and then plus 50 times 1.66. Cool. So what's this times 50? 83 times, no. And then we're going to add it to 250. So heck yeah. So our tension here is 333, which is half of what it, it was 666, you know what I mean? And, but now it's less. So if this whole thing's, and that's what we would expect, because, Yeah, it's kind of fascinating. So here's a scenario. You're holding on to this, setup. And you know what I mean? Hey, you're just standing on the ground. And so you're going to, and it runs, and we already found out that it's 1,333. This tension we got to multiply by 2. Okay. So now let's say you jump off this cliff, and now you're holding on to this setup. And now how much does it weigh in your hand? It weighs nothing. You know what I mean? So the tensions in the string are nothing. The weight is nothing. Cool. So now you're going to step off, harness yourself into a mechanical machine that's on a track that just allows you to fall at half of gravity, half of g. That's just 5 meters per second squared. Sorry about that. When you do this and you're holding on to this assembly, it's going to feel that tension. So this is fascinating. It's like these problems, you must do the technical perspective, because I don't think the tension in the cord is the one thing that's the nonsensical. like it's like, oh, I can get the driving force, because even in this one, now I can come up with my own axiom. And my axiom would be like, hey, if this is you know, kind of if this pulley is static, you know, connected to a wall, yeah, I can see that there's going to be a driving force. Like this is 1,000 newtons and this is 500 newtons. So I'm going to have a driving force of just 500 newtons. You know, not 1,000, but that driving force is going to operate over the total mass of both of these. So I get that. That I can do really fast. And now I can even say that if, and then let's go to the free fall one. If it's in free fall, I would say that there's 0 newtons for driving force. And then if I say acceleration is that halfway, well, hell yeah. This thing's going to have a driving force of 200 newtons. And so it's very similar to this mass not weighing 1,000 newtons and this mass not weighing 500 newtons. But it's synonymous with this, you know what I mean, mass, like the force on it being 500 newtons, and this one is 250. And so then the driving force is 250 newtons. Now, I don't think that's technically accurate because, you know what I mean? We just said Kepler's equation, it doesn't matter. Mass is mass, and you're still going to have that same force of gravity. What makes these appear to be less force is the fact that, you know, that they're moving in a reference frame. But I'm going to actually stop because that's as far as I can get. You know what I mean? I don't want to say anything that's dumb or just confusing, but that's as far as I wanted to get with this problem. I wanted to look at something, so then I could go back to this, and I'd be like, well, if this was falling in free fall, like the force on it, the force would be the force of gravity, which would be mg. Cool, and that would be the driving force. But then I go over here, and this is only like 6.6. So then I would say, well, hey, it looks like the driving force isn't mg. It's going to be 2/3 mg. Like that's going to be the driving force on this thing, because this whole thing is falling at a yeah. So that's kind of interesting. Oh, darn it, you know what I mean? I'll have to revisit this one. You know what I mean? But that's why we're just making this one, which I can totally do start to finish. And so we're going to do, or is that the last scenario that I wanted to do? Yeah, that was it. You know what I mean? And so I think I can use this perspective that, hey, if I have this pulley and I have 50 and 100, and the thing is moving like at 5 meters per second squared, well, it's like these things weigh half as much. And so then the driving force, if it wasn't moving, I'd be like, hell yeah, we got a driving force of 500 newtons. Because this is 1,000 newtons, mg, and this is 500 newtons, mg, driving force of 500. But if we're actually accelerating at 5 meters per second, no, that's going to be a ratio of a half. So what would be the ratio? Well, it would be this acceleration, the acceleration of the frame of reference or whatever, or the mechanism, or, you know, and it's going to be that 5 divided by 10, which is actually gravity. So whatever this AF divided by G is, that's going to be the ratio of these forces. You know what I mean? Kind of the, and I would probably just say, you know what I mean, apparent forces. So then, if I'm in a scenario where, oh yeah, I don't think I've done this problem yet, but I took this rolling thing and said, oh, so it is moving at 6.6, which is faster than our setup. If this is just stationary and we have 150. This thing is moving at an acceleration of 3.3. Like this mass. You just say, hey, look at that mass. It's moving at an acceleration of 3.3. And I don't know if I've done this video. Maybe I have. But what I wanted to do was take this rolling, you know, vertically rolling disc, and then turn it into just a mass on a pulley, and then have it connected to another mass. And what would this mass have to be? If this was 100 kilograms, what would this need to be so it would fall at the same rate? And I think I did make that. You know what I mean? I think I already made that video. But yeah. So I guess to take home, and I think this is going to jive. You know what I mean? But that was just the thing. How do you add in this acceleration? And it seems like very technical. You actually have to add the accelerations, and I think you lose a lot just using this equation. So I mean, from the fundamentals of what's going on. And so that was my whole goal, is to be like, hey, I just want to look at a rotational problem and then find a driving force. And maybe this is just my term, just a driving force. I know it's operating on both masses. I get that. You know what I mean? F drive is equal to the mass total of both of those. And then whatever acceleration, if they're attached to the same thing, those are going to be the same for both. Cool. And yeah. And if this whole mechanism is accelerating downward at 5, well, these forces are going to be half. This is going to be 250. This is going to be 500. If this acceleration is 2/3, well, 2/3 g, just like a rolling thing down a hill or whatever. Well, now these forces are going to be different. It's going to be 2/3. I don't want to get I don't want to confuse this problem in my mind. But yeah. If this thing is falling not at gravity, but it's falling at 0.6 gravity. You know what I mean? It's falling at 6.6 meters per second. It's falling actually pretty fast. So the ratio on these. Oh no, and I have this in reverse. No. So yeah, we definitely have to clean this up, because right here I said this was the ratio. No, this is wrong. Because if this thing's falling in free fall, these effective the forces on these things go to 0, and then your driving force is 0. So that's if your acceleration is 10. So we need something that looks like this, where we have g minus this acceleration of the frame of reference of the frame divided by g. So if this is our ratio, I think we're good to go. Because if we're falling at 10, this is going to be 10 minus 10 divided by 10. So that's going to be 0 divided by 10. Now if it's 5, that's the easy one. That's why this equation didn't pop out. It works for that, but only that one. Because then we have 10 minus 5 is 5 divided by 10. So that's going to be 5 divided by 10 is a half. Yeah. So that would be the. So these effective forces then drop to a half, and so let's drop this thing. Yeah, let's All right, hell yeah. So this is gonna be the moment of truth. We're gonna end with just kind of a technical solution. And we'll be able to do it both ways. I mean, because that was the whole thing of coming up with kind of a quick way. So we have the 50 and the 100, and then we're going to say it's accelerating at 3.3. You know what I mean? And then this is going to be 10 divided by 3. Okay, so now what's our ratio on these? You know what I mean? We know the force is if this was 10, these go to 0. If it's half, then they're half. If it's less than half, then yeah, we have to kind of use that ratio of 10 minus this 3.3, and I have that 3.3. My calculator is a, so we have 10 minus a, and then divided by 10. So now I have this ratio of 0.6. I'm going to multiply. And then I know this force is 500 newtons, and this force is 1,000 newtons if it's stationary. I'm going to multiply this by this 0.6, so I do 500, and I get 333 newtons here, and then 1,000 times B, and then I get 666 newtons, and then I can see that, hey, I have a driving force, just to do these problems just kind of visually, of the difference between these, and obviously it's just 333.3 newtons is the driving force. That driving force is operating on both those masses, and so we do F equals ma, so we have 3, whatever, you know what I mean, newtons, and then that's going to operate on 150 kilograms, and we find the acceleration. So it's just divided by 150, and so we have the acceleration is this divided by 150, and we get an acceleration of 2.2 meters per second squared. Sweet. So, you know what I mean? Hell yeah. So that was just a couple steps, and that really shines of like how this could be a really good solution. So now we're going to do it technically. So we have a tension there. We have a force down of 500 newtons. We have this one. We have a tension up. We have a force down of 1,000 newtons. We're going to say this is the positive direction. This is the positive direction. So on here, this is the positive, and then this is positive. So for this equation, I'm going to say t minus 500 is equal to this 50 times the acceleration, and we see that it's the frame of reference is accelerating in the wrong direction, the negative. So we have negative 3.3, and then we have plus. Hey, it's probably going this way around, so we have that A. And now we're going to do this one. So we have 1,000 minus t is equal to 100. And then this one is going in the right direction of the frame of reference falling, so it's 3.3 plus, hey, and it might be going, this thing might be accelerating around this pulley, so we have that A. We're going to add these two equations to get rid of the t, so again we have 500 is equal to, so now we're going to have 50 times alpha A, so we're going to have this, we're going to have, now alpha A in my calculator is just this 3.3. Not to confuse this acceleration as A. So we have 166.6 plus 50A. Oh, and I was supposed to do it over here, but yeah, let's do 166 plus 50A, and then here is going to be 333 plus 100A. So now we're going to add these. We get the 150A. And we get this plus, how the hell do I do this? This times 1,000. No, this times 100. Cool. So these add up to 500. Does that make sense? There's 4, and then there's basically 9. Yeah. So 500. So cool. So we get 500 on this side of the equation. So we have 500. Oh, did we bound this up? I feel like we messed it up. This is negative. Yeah. Holy Toledo. Sorry about that. Yeah, negatives kill me all the time. Yeah, and that was kind of the most interesting thing about this problem. That was probably the hardest thing. Is to see that, hey, you can add the acceleration components. This one, due to it in free fall, is going to accelerate in what we're calling the negative direction. This one is going to fall that same way, but we're going to call that the positive direction. So positive and negative. And so now we have this being negative. And now we're going to add it to that. And then so we just get 166.6 plus 150A. And now we're going to 500 subtract this. So we got 500 subtract that. And then divide by 150. So A is going to be this divided by 150. And we get 2.2. Alright, so that was the technical way to do it. But you see, it's like, man, that's a lot of algebra. 2 equations, 1 equation, 2 equations, 2 unknowns. Oh, yeah. That was the other thing that we didn't... Yeah, no, we solved for the tension in this one. So let's solve for the tension in this one. This one was, when one of the ropes, it was 333 newtons. In both, it was 666 newtons. So if this is falling at half of gravity, hey, you're not even feeling, out of the 1,500 newtons that you would feel if it was like balanced. The only way it's going to be balanced is if they're both 75, and on the, if these are both 75, then you're going to feel this 1,500 newtons. But in our scenario, when it's moving half of g, half of gravity, then yeah, you're almost experiencing a third. What is that ratio? 666 divided by 1,500. You're experiencing 44.4% of the weight that you would actually feel. Okay, hell yeah. So in this one, let's solve for tension, and we can say that tension. Well, what's the nicest equation? None of them are nice. So we're going to do tension is 500 plus 50 negative 3.3 plus A is 2.2. Cool. So we have that. We're going to store this as alpha C. Alpha A, we're going to do negative alpha A stored as alpha D. Cool. So we have alpha C and alpha D, and we can say 500 plus 50 alpha D plus alpha C. Hell yeah. So we get a tension of 444 newtons. Obviously, it's going to be a little bit bigger than this acceleration was 5. This acceleration we want to do 3.3. So we're experiencing more tension. Divided by 1,500, yeah, now we're experiencing basically 30%. 30% of the weight of if it was a statics problem, and both of them were 75. Okay, so this method was very useful. You know what I mean? Hey, finding the driving forces, but knowing that you might have your frame of reference might be accelerating, and then so what's the equation? And I think we did that nicely. So hell yeah. That was kind of a fun way to, and hopefully I'll use this, but man, this was really hard to even think about this evening. So I'm glad I made this video, and heck yeah, thanks for joining me, and that's a video.